On to the chapter Chemical Equilibrium. A process starts of its own and on initiation continues for some time with falling rate and ultimately stopping. Although the reactants are still there, but they don't appear to react anymore. In such a situation, the process or the reaction is said to attain equilibrium. The composition of a reaction mixture at equilibrium at a given time is same, irrespective of whether we start from the reactant side or we start from the product side. In a general reversible reaction where A and B react to give the product C and D, with the passage of time, the concentration of reactant A and B decrease. Therefore, the rate of forward reaction decreases as is shown by the red line. On the other hand, the concentration of product increases. Therefore, the rate of a backward reaction increase as is shown by the green line. A stage is reached when both the backward reaction and the forward reaction become equal. That is, the rate of forward reaction and the backward reaction are equal, and such a state is known as the state of equilibrium. Thus, the state of equilibrium is a state in which the measurable properties of the system do not undergo any noticeable change under a given set of conditions. That is, the properties like concentration, pressure, etc. of the system become constant. But it does not mean that the reaction is stopped. Both the forward and the backward reaction continue even after the attainment of equilibrium. However, the rate of the forward and the backward reaction become equal. The law of mass action, it states that the rate at which a substance reacts is proportional to its active mass. Active mass is the molar concentration. And the rate of a chemical reaction is proportional to the product of active masses of the reactants. Thus, in this equation, where A and B react to give C and D, and the rate constant of forward reaction is K1, whereas rate constant of the backward reaction is K2. Thus, the rate of forward reaction R1 is equal to K1 into concentration of A and B, whereas rate of the backward reaction R2 is equal to K2 into concentration of C and D. At equilibrium, when both the forward and the backward reactions are equal, that is, K1 into concentration of A and B is equal to K2 into concentration of C and D. Rearranging it, we get K1 upon K2 is equal to concentration of C and D divided by concentration of A and B. This ratio, that is, the ratio of forward reaction and the backward reaction rate constants, is equal to Kc. Kc is equal to rate constant of forward reaction divided by the rate constant of the backward reaction. And Kc is the equilibrium constant of the reaction. Let me take another reaction where A moles of A and B moles of B react to give C moles of C in D moles of D with rate constant of forward and backward reaction being K1 and K2 respectively. Here, the equilibrium constant we get is concentration of C raised to the power of C multiplied by concentration of D raised to the power of D divided by concentration of A raised to the power of A and B raised to the power of B. If the reactant and product both are in the gaseous state, it is more convenient to use partial pressure instead of the concentration terms. Thus, we can replace Kc with Kp, where Kp is equal to partial pressure of C into partial pressure of D divided by partial pressure of A and partial pressure of B. According to ideal gas law, where PV is equal to nRT, we can rearrange for the partial pressure P is equal to N upon VRT, where N upon V is equal to C or the molar concentration. Thus, the partial pressure of A is equal to CRT, partial pressure of B is equal to CBRT, partial pressure of C is equal to CCRT, and partial pressure of D is equal to CTRT. Thus, Kp, which in equation 1 is equal to Pc into Pd upon Pa into Pb, we can replace Pc and Pd by the equation CRT, and we get Kp is equal to Kc RT raised to the power of C into, we get Kp is equal to concentration of CRT raised to the power of C into concentration of DRT raised to the power of D divided by concentration of A raised to the power of ART raised to the power of A and concentration of B RT raised to the power of B. Rearranging and bringing the concentration terms together and taking RT common, we get concentration of C raised to the power of C into concentration of D raised to the power of D divided by concentration of A and concentration of B multiplied by RT raised to the power of C plus D minus A plus B, where C and D are the moles of reactant and A and B are the moles of product. Thus, we come to the relation Kp is equal to Kc. This whole term is equal to Kc, which is equal to this one. It can be replaced by Kc and Rt raised to the power of delta n. Delta n is the difference of moles of product and the reactant. So equation 2 is the relationship between Kp and Kc. That's all.